Right. Comparison tests. See, when you are given two series of positive terms, let us say like summation un and summation vn. When you are given two series of positive terms like this, when you know the convergence of one series, depending on that, we can find the convergence of the other series here. If you look at this, you see, for these two series of positive terms, if they are following this particular condition, like un is less than or equal to c times vn, for all n belongs to n, then you see if vn is convergent, then we say summation un is also convergent. Understand what it is exactly. You are given two series such that for all n, one series is completely less than the other one. Of course, some constant times the other one. And you are given this vn is what you call convergent. Look at this. Un is a smaller series, and vn is a larger series. When a larger series itself is convergent, what do you mean by convergent? This summation vn approaches to what you call a finite value. When a larger series is approaching to a finite value, it's obvious to understand even a less smaller series will also approach to finite value. In that sense, you see, when vn is convergent, before that you see when un is completely less than or equal to c times vn, then when summation vn is convergent, when a larger series is convergent, then obviously a smaller series will also be convergent only, right? Like this, when one series, by comparing it with the other one, you can give a conclusion about the other one. In a similar way, in fact, if you look at this, you see, when you are given these two positive term series, and if they are like un is greater than or equal to c times vn, understand it this way. Now in this case, when one series is completely more than the other one, c times the other one. Now in this case, you see, if this series vn is divergent, understand what you mean by divergent. This summation vn approach to what you call infinity. Look at this. Vn here is a smaller series and un is a larger series. When a smaller series itself approach to infinity, can't you expect this larger series will also approach to infinity only. So with that sense, you see, when summation vn is divergent, when a smaller series is divergent, then obviously the larger series is also divergent. So this is how we can have one type of comparison. And the other one, you see, which we more popularly use, limit form, limit comparison test. Look at this. See what we are doing in this. When you are given two series of positive terms like summation un and summation vn, for these two series of positive terms, we define what you call a limit here like this. You see, limit n tends to infinity un by vn. If this limit is a finite non-zero value, look at it. This limit, it must be a finite and that to non-zero value. Then we say summation un and summation vn both behave alike. You are actually choosing one series whose convergence is already known to you, right? Here, this summation vn, we call it as auxiliary series whose convergence is already known to you. Now, to identify the convergence of this other series summation un, in fact, we are using this summation vn here. And you see, in the process, we are actually defining a limit n tends to infinity un by vn. And if this limit is a finite non-zero value, then we are saying summation un and summation vn behave alike. It means whatever the series we have already considered, right, whose convergence is already known to you, if that series is convergent, then obviously this other series, it is also convergent. In case if vn is divergent, we can say even un is also divergent, right? So always these two behave alike, they behave similarly. When this limit is a finite and non-zero value, you can understand when the limit will be zero normally, either this vn is infinity or un is zero. In either cases, the limit will be zero. But you see, understand it that way. When vn is infinity and un is zero, understand when vn approaches to infinity, it is a divergent series normally. And when un approaches to zero, it is a convergent series. So when you have two different series, you will get normally the limit as zero. And of course, there are cases where you may get the limit itself as infinity. In all those cases, we cannot decide anything about the convergence of un. But when the limit is finite and non-zero, in that case only we can decide these two as, these two behave alike, right? So keeping this simple idea in mind, in comparison test, we are first going to choose one series summation Vn such that, its convergence is already known to you. And using that, you see, we are going to decide the convergence of the other series. Okay, so let's take a question. And let me just add a point here before going to the question. How to choose this Vn? See, for example, you are given one positive term series summation Un whose convergence is to be calculated, right? I mean, we need to decide whether this series is convergent or not. For that, you see, we need to consider what you call the nth term, let us say Un, right? After identifying this nth term, we need to just write it as, some function of 1 by n by taking certain terms common out of this. So that you see here, you will get something else, right? As the coefficient of this function, right? Whatever the coefficient we get here, you see, this coefficient, we take it as, Vn, right? So that after defining this Vn, I hope you remember frequently, more popularly, more generally to say, whatever the Vn we choose, this Vn follows either geometric series or what you call P series, right? Using these two series, we will decide the convergence of this, selected Vn here. And then, of course, we'll just evaluate this limit and see whether those two behave alike or not. Okay, so that's the main story. And now let's move on to a question. Let's look at this question. Test the convergence of the series 1 by 1 into 2 into 3 plus 3 by 2 into 3 into 4 plus 5 by 3 into 4 into 5 and so on. Look at this. When you are given a series of this kind, the first thing is to identify the nth term, right? That is the most important part of this. Once if you identify the nth term, the remaining story is quite simple, right? Look at it. Because, they're all, what you call rational terms here. I'm only looking at the numerators. Look at the numerators. In the first term, it is 1. In the second term, you see, I mean, when n is equals to 1, I mean, in the first term, it is 1. Then in the second term, I take n is equal to 2. See, in the nth term, we have the numerator as 3. Then when n is equals to 3, see, we have this as 5. See, what are all these? These are all simple odd numbers. Look at them, right? They're all odd numbers, or, they're all in arithmetic progression with a difference of 2. So when they're all odd numbers, I hope, you must remember always, when you have one number n, and if you multiply this number with 2, it becomes 2n, this 2n is always an even number, right? So when you add or subtract a number from this, I mean, when it is 2n plus 1 or 2n minus 1, they become what you call odd numbers, right? Otherwise, see, this is all, this is all a set of numbers which are in arithmetic progression. With to find out, nth number in this arithmetic progression, we use this idea, a plus n minus 1 into d. And here you see a is the starting number of the series. So it is then 1 plus n minus 1 into c. The difference of any two successive numbers, it is 2. So even if you simplify this, we'll get it as what you call 2n minus 1. Right? So it's clear now. By looking at the given series, one can easily understand the numerator is 2n minus 1 in the nth term. Now look at the denominator. Look at the only first terms, right? First, because, they are in product in the denominator, 1 into 2 into 3. Next term low, what you call 2 into 3 into 4. Then, in the third term, we have 3 into 4 into 5 and so on. Now, if you only look at the first term in this denominator, product of the denominator, in the first term, we have 1. In the second term, we have 2. In the third term, we have, 3. So if you continue this idea, in the nth term, obviously, we must have n only. So it will be n only. Then if you look at the other two terms, you see 1 more than this first one and 2 more than the second one. And here also, see the same thing, 2 plus 1 and 2 plus 2, 3 plus 1 and 3 plus 2. The same way in the nth term, when the first one here is n, the next two terms are obviously n plus 1 into n plus 2. Fine. So that's clear. This is absolutely now the nth term. Now, once after you identify the nth term, as we discussed already, we need to rewrite it so that, we should get a function of 1 by n from this. So I'm just trying to take some of the terms common from them. You see, from the numerator, I'm trying to take what you call n common from the numerator because I'm trying to get 1 by n. So it is, when you take n common from this, we'll get it as 2 minus what you call 1 by n. Fine. Then already here is 1 n. I'm just writing that as it is. Now from the other terms also, because we are always we are expecting simply what you call 1 by n everywhere. So let me take n common from this also. So it is n into 1 plus 1 by n. Then here also if you take n common, we'll get 1 plus 2 by n. So this is equals to, see what we can do here. 1 n can be cancelled out. So what remains? 2 minus 1 by n divided by, look at them. Here we have 2 n's. If you multiply them, we'll get first of all n square, then 1 plus 1 by n, then 1 plus 2 by n here. Right? Look at them. For more convenience, you see I'm writing it again like this. 1 by n square, I'm writing it aside. And the remaining things I'm writing in bracket, you see like this. 2 minus 1 by n, in the denominator, 1 plus 1 by n multiplied by 1 plus 2 by n. So now if you look at these terms in the bracket, they're all simply functions of 1 by n, isn't it? When they're all functions of 1 by n, you see whatever the coefficient you get here, like 1 by n square in this case, that function is now Vn for us. Okay, so looking at that particular coefficient of this function of 1 by n, we need to decide what you call Vn. So in this case, the coefficient what you get is 1 by n square. So let us take that 1 by n square as Vn. So let Vn is equals to 1 by n square. So when we take 1 by n square as Vn, we need to choose summation Vn. Look at it, when it is summation Vn, we should write it as like 1 by n square. When it is 1 by n square, you should recall immediately what you call P series. Right? What P series says is, when you have summation 1 by n power p, depending on this power p, we have convergence. Like the series, we say it is convergent when p is greater than 1, and we say the series is divergent when p is less than or equals to 1. Keeping these things in mind, we are going to decide whether the summation Vn is convergent or not. Okay, now see, look at this power p, it is 2 here, and that 2 is clearly more than 1. So keeping that power in mind, we can say summation Vn, I mean summation 1 by n square is clearly convergent from P series. So keeping that in mind, you see I'm writing this from P series, summation Vn is equals to summation 1 by n square is convergent. Right? Now see, this is our auxiliary series whose convergence is already known to you. Why this is convergent? This is because the power p, n power p, is greater than 1. Okay. Now see, we got one series whose convergence is known to us. Now to identify the convergence of actual series summation un, right? So actual series summation un, let us define what you call the limit, right? So now let's consider limit n tends to infinity un by vn. Let us see how much it is. Limit n tends to infinity. Let me write what is un. I'm just writing all these things here. You see what you have there, 1 by n square multiplied by, I'm just writing, this is un, right? After taking, all kind of comments and, after simplification, I'm just writing that. We have, you see, 2 minus 1 by n divided by, in the denominator, 1 plus 1 by n into 1 plus 2 by n. Right? This is all un, and this divided by what you have is vn. How much is vn? You see, 1 by n square. So I'm writing that 1 by n square also. It's clear, you see, easily you can understand this 1 by n square can be cancelled out. So when 1 by n square can be cancelled out, what remains here? You see, only this much. Now, as you know, as n tends to infinity, you see, this 1 by n approaches to 0. In fact, not only here, even in the denominator, 1 by n or of course this 2 by n, both approach to 0 only. So what remains here, you see, as n tends to infinity, in the numerator, it is 2 minus 0, 2 divided by 1 into 1 only. So in simple, you can understand the limit what you get here is simply 2, and that too, it is a non-zero value. Right? Therefore, you see, from limit comparison test. Right? See, we have already discussed it. From limit comparison test, when the limit n tends to infinity un by vn is a finite non-zero value, we say both summation un and summation vn behave alike. Right? What do you mean by this? If summation vn is convergent, then summation un is also convergent. See what you got earlier? For this auxiliary series from P series, we already got, summation vn is convergent. Since summation vn is convergent, summation un is also convergent. Right? So like this, by taking the limit, we need to identify whether the given series is convergent or not using limit comparison test. Now let me just give you one more example so that you will understand the things very easily. Look at this question. Summation n is equals to 1 to infinity, n plus 1 into n plus 2 divided by n square root n. Right? This time, you are already given nth term. So I'm just giving you the answer directly. Yeah. If you take, this as un, let summation un be the given series as usually. And if you take this as un, see what you'll get here. See what it is? When you have un, see all this is un. As we did in the previous problem, by manipulating un, I mean by rewriting it as some function of 1 by n, we are going to decide what you call 1 by n, what you call this vn, correct? So to get a function of 1 by n here, as we did in the previous problem, I'm taking n common from the numerator again here also. So from this first n plus 1, if I take n common, I'll get 1n. And then even from n plus 2, if I take an n common, I'll get one more n. So when you take n common from these two terms, you see, we'll get it as n square. Correct? It is n square. And then what remains there in the numerator? It is 1 plus 1 by n. And then here also it is 1 plus 2 by n. Now in the denominator anyway, they're all simple independent functions. So I'm writing them as they are. N square and of course root n. Now as you know, this n square can be cancelled out. Right? So n square can be cancelled out. And what remains you see here? I'm writing this 1 by root n here aside. Then the remaining terms 1 plus 1 by n as well as 1 plus 2 by n. Now see, as we discussed, this is all a function of 1 by n. This product of last two terms 1 plus 1 by n, 1 plus 2 by n is a function of 1 by n. And whatever the coefficient you got here, you see 1 by root n. That 1 by root n can be taken as vn. Okay. Now see here what happens. If you now take this vn, if you now take this vn as 1 by root n. In fact, as you know, we can also write this root n in the denominator as n to the power of 1 by 2. So that the series becomes now summation vn. And as we know, when it is summation 1 by n to the power of p, and if that p is less than 1, we know the series is a convergent series, right? And here that p is, because the power is half, n to the power of half is there, you see. Since that half is less than 1, we can say this series summation vn is a divergent series. Okay. Now we have one series summation vn whose convergence is known to you. I mean convergence or divergence is known to you now. Correct? Now, after identifying such a series, we need to take the limit form. So as we know, as we did in the previous problem, here also limit n tends to infinity, I've considered it as un by vn. Right? It is quite clear. I've just substituted, un. All this un I've substituted in the numerator. And in the denominator, you see vn, whatever we discussed, it is 1 by root n. It's clear, you see, we can cancel these two terms now. Right? Now, after cancelling them, what terms remain here? It is 1 plus 1 by n and then 1 plus 2 by n. As you know, when n approaches to infinity, both 1 by n as well as 2 by n approach to 0. That's how we'll get the limit as 1. In comparison test, we want the limit to be finite and non-zero. Even if it is 1, we don't have any problem. So since we got it as a finite and a non-zero value, we can say both summation un and vn behave alike. And since already summation vn is divergent here, we can say summation un is also divergent. Right? So like this, we can answer a question. I mean, we can decide the convergence of a series using limit comparison test. And one can ask me, what if such a Vn doesn't exist? Then you can say, and one more thing, what if this Vn doesn't exist, or what if the limit is equal to 0? In either cases, you can understand we cannot use limit comparison test to conclude the convergence of this particular series. Probably we have to use some other tests, whatever are available. Okay. In fact, as you know, we cannot give the convergence of every series by every technique. There are different techniques uh, which are suitable to different series. Okay. So we will only choose a series which is suitable to that particular series. Always we'll only consider different techniques which are suitable to that particular series. Right. Now let me just move on to one more question. Look at this. Now we need to discuss the convergence of this series. Summation n is equals to 1 to infinity square root of 3 to the power of n minus 1 divided by 2 to the power of n plus 1. Now see, keeping that in mind, easily you can understand what is un here. Un is square root of 3 to the power of n minus 1 divided by 2 to the power of n plus 1. As we did in the previous two problems, we need to write this as a function of something like 1 by n. Okay, right. Keeping that in mind, you see what I'm trying to do. Anyway, because this n is now in the power, we won't get directly 1 by n, but that function of n should come in the denominator. That is the main story. 1 by something, some function of n in such a way. So for convenience here, I'm just writing numerator and denominator separately here. I'm writing it as square root of 3 power n minus 1 divided by square root of 2 to the power of n plus 1. So when I write this separately, I can take the terms common quite easily. Then you see the function of n, 3 power n, I'm taking that 3 power n common from the numerator. When I take 3 power n common from the numerator, you see, I'll get in the second term here 1 by 3 power n, right? So that I'm getting that function of n in the denominator. So as n tends to infinity, that goes to 0. That is the idea. So when I take 3 power n common from this numerator, it comes out as square root of 3 power n. Fine. So when I take 3 power n common, the remaining terms are square root of 1 minus 1 by 3 power n. In a similar way, in the denominator also, I'm taking 2 power n common. So when I take 2 power n out of this, it comes out as square root of 2 to the power of n, and the remaining terms you see 1 plus 1 by 2 to the power of n. Fine. Then for convenience, as you know, when it is square root of 3 power n, in fact, when it is like square root of a, we can actually write this as a to the power of 1 by 2. Moreover, in case if you have a to the power of m, square root of a to the power of m, then what happens to this? It is a to the power of m whole to the power of 1 by 2, right? The square root can be written as power of this a power m. Fine. So when you have this kind of index, how can we write this then? It is a to the power of, I hope you remember this, a to the power of m in a to the power of m whole to the power of n can be written as a to the power of mn. So with that idea only, here we can write it as a to the power of m into half as a to the power of m into half, which is m by 2. So keeping this idea in mind, we have written square root of 3 power n as 3 to the power of n by 2, right? In fact, even in the denominator also, we have the same thing. So that's the idea there. We got 3 to the power of n by 2 in the numerator and 2 to the power of n by 2 in the denominator. The remaining things, I've written them as they are. Now see, we have same powers in both numerator as well as the denominator, 3 power n by 2 as well as 2 power n by 2. So we can write these two together, you see. That's how I have written it as 3 by 2 whole to the power of n by 2. And of course, the remaining terms, they simply remain as they are. Now from here, you see, this is a function similar to a function of 1 by n. This is one function which is very much similar to a function of 1 by n. Correct? Understand, we may not get every time 1 by n, but this function of n should come in the denominator. That is the main idea. And if you get it like this, as n tends to infinity, this whole term 1 by n or 1 by something goes to 0. Okay, so we got exactly a function of this kind, and its coefficient, look at this. We take this as what you call Vn now, right? So as you can see here, right? If I take this as Vn, 3 by 2 whole to the power of n by 2. In fact, you see, for your convenience, we can also write it like this: 3 by 2, as I told you a few minutes ago, when you have a to the power of m whole to the power of n, it is a to the power of mn, right? So the same for our convenience. Now we are just going it back, right? See, you have actually this much: 3 by 2 whole to the power of n by 2. We can actually write this as 3 by 2 whole to the power of half, and this whole to the power of n, right? It's like again a power m whole power n. Fine. When it is 3 by 2 whole to the power of half, it can be written as square root of 3 by 2 and this whole to the power of n, right? Now see why I am writing it this way. The question comes obviously. See, we got exactly two standard series. One is P series and the other one is geometric series. Anyway, it's clear it's not like 1 by n power p. If you have, the series as 1 by n power something, we would have used what you call P series to decide its convergence initially, right? To decide the convergence of auxiliary series. But it's not exactly in P series form, right? So if you look it carefully, it is, almost like a geometric series. But to be in geometric series, it should be like this, summation r to the power of n. Whatever may be the r here, that is okay. But you see, you should have a power n here. So to get a power n from here, you see, we are rewriting it. What you have here actually power n by 2. I'm bringing that power 1 by 2 inside this, so that I got square root of 3 by 2 whole to the power of n. Then I can take this r as, square root of 3 by 2. Okay, that's the basic idea here. Now, if you look at that carefully, by taking that r is equal to 3 by 2, you can understand it is clearly a geometric series, right? Of course, depending on the value of r, we will decide whether it is convergent or not. That we'll see anyway now. Now, that's how you can see this summation Vn is a geometric series with common ratio root 3 by 2, right? As we know, for a geometric series, if that r is less than 1, we say it is a convergent series. And if when r is greater than or equals to 1, we say it is what you call a divergent series, correct? That's how you see, since root 3 by 2, root 3 by 2 means, root 1.5. As you know, square root of 3 by 2 means 1.5. As we know, root 1 itself is equal to 1. Root 1 is itself equal to 1. When you have a value which is more than 1 here, obviously we'll get this as more than 1 only, right? Maybe very less, but definitely more than 1, right? That's how this root 3 by 2 is greater than 1. And from geometric series, we can say, since this r is greater than 1, summation Vn is a divergent series, right? So we got a divergent series. I mean, the auxiliary series has a divergent series. Now, to decide the convergence of actual series, I'm taking the limit form. Limit n tends to infinity, un by vn. As we know here, you see, one can easily understand here actually without writing also. All this is vn, right? All this is, all this is un. If you look at only this term, if you keep this aside, the remaining here is just vn only. Whatever the vn we have assumed here, correct? Now, in the limit form, you are dividing all this by, its coefficient. So if you divide all this term by this particular term vn, obviously what remains, it was written here. Square root of 1 minus 1 by 3 power n divided by square root of, this particular term only remains there, right? And for that, that's how, I'm just telling you that, though you can understand here, 3 by 2 whole to the power of n by 2 divided by root of 3 by 2 to the power of n. You can just cancel, these two terms. That's how, we got only the remaining terms, whichever is highlighted here. That's what you get here. And as n tends to infinity, as you know, this 1 by 3 power n or 1 by 2 power n, both approach to 0. That's how we'll get the limit as simply 1. Root 1 minus 0 by root 1 plus 0, which is root 1. Anyway, we are taking the limit as 1 because the series what you have considered is a positive term series. So this is again, you see, we got the limit as 1. It is again finite and non-zero. Since it is finite and non-zero, we can easily understand both un as well as vn behave alike, right? That's how you can understand, since these two behave alike, we can say summation un. As you know, summation un is already a divergent series. We have already identified this. Since this is a divergent series, we can say un is also a divergent series, right? So like this, from the given series, by taking a little manipulation, we need to identify an auxiliary series. And for that auxiliary series, we need to identify the convergence either from P series or from geometric series. After that, by taking a limit form, if that limit is a finite and non-zero value, then we say the convergence. We'll just conclude about the convergence of given series, right? So this is how we just solve problems using what you call limit comparison test.